Welcome back, Nicholas and Shania. Hopefully Shannon will be back soon. Right, last week we actually had a question, and I can't remember who asked it. It was in connection with the melting points of solids and the group 1 metals in particular. Because as you can see on the screen here, remember we have the macroscopic, the microscopic, well, by that I mean the submicroscopic. We can't see it, so we just trying to explain what we can see. So if you like, that's the fact. Okay, this is the theory down here, and then we have the model, which could be equations, formulae, diagrams, and so on. Okay, now there was a question of why do metals have low melting points with respect to the group 1 metals, and so that's our macroscopic. It's a fact, you know, we do the melting point, so we've got to try and explain it. And it's in two things really. It's in connection with the number of valence electrons. How many valence electrons does group 1 have? 1. Correct. So there's attraction just simply to the between the nucleus and 1 electron. And of course those electrons can move around, so the electrons keep on changing, but it's pretty much just that 1 attraction. Compared to aluminium, that has 3, so it's got a higher melting point as expected. So that's the first thing that affects it. And then the second thing is, you'll find that, and I just looked it up, so we've got the facts. Lithium has a melting point of around about 180, sodium 97, potassium 63, and cesium is pretty much a liquid at room temperature. I mean, it melts at 28, so it's got to be a hot day, but then it can go into a liquid. So as we go down the group, and I think I might actually just make this bigger so you can see what I'm talking about. So these are lithium, the sodium, and the potassium. Okay, I'll just draw on it. So we've got, okay, lithium over there, and then going down to cesium down here, which is only 28. And that's what happens is, as we go down, we get more and more energy levels. So for instance, you know, how many energy levels does hydrogen have? Thinking of the electronic structure, we did, it's 1. Right. Lithium, how many energy levels does lithium have? 2. And so how many do you think sodium is going to have? 3, correct. And you can see how we're going down, 4, 5, 6, 7, and so on. So what's happening, if my nucleus is here, every single time my valence electrons are in a shell further away. So you know from two magnets, if you hold two magnets close together, there's a strong attraction, but if you pull them apart and they're further apart, that attraction isn't as strong. So the further away that valence electron is, the weaker the attraction. And not just that, you've also got all those electrons in the inner energy levels that sort of interferes. It's like having a fridge magnet, and it can hold up one piece of paper without a problem, but you try and hold up 2 or 3 pieces of paper with that fridge magnet, it'll just fall down because the attraction is too weak. So if you have things interfering between the nucleus and the outermost electron, that is going to reduce the amount of attraction. So is that clear why group 1 metals have a much lower melting point and why the ones down at the bottom are so low? As I said, it's slightly different to this over here, these really heavy ones, because over here you get a whole lot more coming in. You can see it changes from 57 to 72. So these are getting quite heavy, so there are other factors that come into play. Okay, right, so let's go back to our slideshow. Okay, so what we want to focus on now is the molecular solids, but let's just quickly go over our solids we've done. So you've got to know these off by heart: ionic, metallic, covalent, and molecular. Okay, and these are the macro properties. Ionic solids are brittle and hard and so on, and you must be able to explain all of those properties. Metallic solids are shiny, lustrous, and so on, malleable, ductile, and so on. Covalent network solids, pretty much the only property that sort of goes across all of them is that it's got a high melting point. Depending on their structure, they can conduct electricity like graphite, or they don't, like diamond. And as I say, if it contains a carbon or a silicon, then it could form these networks if most other elements can't do it. So if you're trying to work out, is it a covalent or a molecular solid, then that's one way of having a look. And then the molecular solids tend to be low melting points, so they're often gases and liquids. So you've got to now, we've explained all these others, you've got to explain now the molecular solids. So the way we explain it in the submicroscopic properties is what particles do we have in that solid and what's the attraction between them. So let's do a quick revision. Ionic solids. What are the particles in ionic solids? Ions, okay, cations and anions, right? And what is the type of bonding between those ions? So a few of you are typing. Okay, it stopped. Okay, right. What we've got? Okay, so those were just the pictures of it. We've got ionic bonding. Okay, right. Metallic solids. What are our particles in metals? So Michael is typing, and this, as I say, it can be fairly debatable because I just want to move on. So metal solids would be metal ions and delocalized electrons, or metal atoms and delocalized electrons. I think what Michael said there is perhaps the best way. So don't, yeah, you could say metal cations if you like, but that anything sort of relating to that, you could say metal atoms, I think should also be accepted. And then of course it's metallic bonds. And for covalent, it's non-metal atoms only, and covalent bonds. Now all of these three bonds are strong. Ionic bonds, so they're all electrostatic attractions. Here it's between a positive cation and a negative anion. Metallic bonds is between the positive core metal ion and the negative delocalized electrons. With the covalent bonds, it's between the nucleus of one atom attracting the shared electrons between the two atoms. So it's both its electrons and the electrons that's being shared from the other atom. Okay, and the final substance is a molecule, is molecular solids that consists of molecules, and we have intermolecular forces between them. So inter means between. So have any of you got an intranet? If you go to a face-to-face school, I'm just trying to compare an intranet to an internet. So have any of you come across an intranet? No, none of you? Okay, I know, like in our home we've rigged up so that we've got cabling between all our computers at home. So that's an intranet. Nobody else can access it. It's just in our home. And in a school there may be a school intranet, which, you know, it's all cabled in for that school. Internet is between the places. So it's an internet is between my computer here and then to where you're sitting in all your different homes or wherever you are. So can you see inter is between things? So it's between the molecules. So I don't know if that will help you remember what intermolecular is, between the molecules. So the first thing I want to ask is, what is a molecule? Because I think we know what cations and anions are in non-metal atoms, but what is a molecule? Does anybody want to have a guess? So I see Michael is typing. Okay, so hopefully non-metal atoms covalently bonded together. Correct. Now, there's one more thing you need to say with that, Michael, and I know you were typing quickly because you were trying to get it down. You have to say you form discrete units. The reason being, what you've said there could equally apply to a diamond, couldn't it? Because carbon is a non-metal atom, covalently bonded together. So we have to use this word, something like discrete or separate. Now, discrete here doesn't mean that you don't, you're not scandalous or anything like that. It's not this C-R-E-E-T. That discrete here means separate. So it's a separate group of atoms covalently bonded together, and they tend to be non-metals. If you Google what is a molecule, you'll get all sorts of answers, particularly in America. And I know there was a Twitter storm among scientists debating what a molecule is, but we're going to stick with this because then I think it makes the intermolecular forces easier to understand. Okay, so examples. These are all molecules, and I've done it the space filled, so you can sort of see what they probably look like if we could see them. And here I've shown it the ball and stick model to show what the sort of bonding is between the atoms within the molecule. So what sort of bond have I got here and here and over here? Is that a covalent bond or an intermolecular bond? Those are covalent bonds. Now, when I melt a substance, do I break these covalent bonds? In other words, this is carbon tetrachloride, okay? If I broke this CCl bond, would I still have carbon tetrachloride? What I'm trying to say is, when you melt something or boil something, then you don't break the covalent bonds, because if I break a covalent bond, I'm not going to have that substance anymore. So if I broke that double bond in oxygen, I'm not melting it, I'm doing a chemical reaction. So the properties of melting point and boiling point is not dependent on the covalent bonds, but it's dependent on the attraction between this molecule and another ethanol molecule. Okay, so if I looked at the boiling points of these molecules, you can see they're pretty low, much lower than the metals, aren't they? And ionic substances. So these are liquids at room temperature because they boil at 78 and 76, and these are gases at room temperature. So let's try and explain these facts. So remember the macro, then the micro, and then the model. So the first thing we do is we have to work out, are they polar or non-polar? Because the types of molecular forces, intermolecular forces, is going to depend a bit on that. Now, can you see that oxygen is non-polar? So go back to what we had discussed in other lessons about Lewis structures and shapes of molecules and symmetry. So can you all see that it's non-polar for oxygen? Yep, okay. What about methane? Methane has got two different elements, carbon and hydrogen. So we've got polar bonds here, but I've said it's non-polar. Why is it non-polar, the molecule? It's got polar bonds, but the molecule is non-polar. So this is just good revision of what we did earlier about shapes and polarity of molecules. So a few of you are typing. Okay, right, because the atoms are evenly spaced around the central atom, so they cancel each other. Okay, just be careful about the pronoun of they. I mean, as I say, I know you're rushing to type in a lesson like this, but try and avoid pronouns because they're ambiguous. Do you mean the atoms cancel each other? It's really the bond dipoles cancel each other. But, you know, otherwise you got the right idea. Ammonia is polar because the atoms are not symmetrically arranged around the atom, around the nitrogen atom. So it's got nitrogen has got a lone pair on this side. So the bond dipoles don't cancel out, so it's polar. We also have hydrogen bonded to a nitrogen, and that's important, which we'll talk about later. This molecule is polar because we've got bond dipoles are all along here, particularly between the oxygen and the carbon and the oxygen and the hydrogen. And this molecule is not symmetrical, so the bond dipoles don't cancel out. And again, important to note for just now, we've got a hydrogen attached to an oxygen. So here we had a hydrogen attached to a nitrogen. There we've got a hydrogen attached to an oxygen. And then finally, this is like a very big version of methane, but I'll use this to contrast. It's non-polar because we've got atoms arranged symmetrically, these chlorine atoms, but it is has a much higher boiling point. Just looking at what I've tried to show there, why do you think carbon tetrachloride has got a much bigger melting point or boiling point? So I've tried to show it in the diagrams. What is the difference between methane and carbon tetrachloride? So some of you are typing. Okay, because it has more covalent bonds. Actually, Michael, not really. Methane has got 4 covalent bonds between the C and the H. There are 4 CH covalent bonds. And here in carbon tetrachloride, there are 4 CCl bonds, but there are still 4 covalent bonds. So it's not the number of covalent bonds that make the difference. It's the mass. Correct, Nicholas. And I was trying to show here the size. You can see this carbon tetrachloride is way bigger than the methane. And because it's way bigger with a lot more electrons and protons and so on, it's a much higher mass. And so it's got more electrons to move around and cause interactions with other molecules. Because remember, electrons aren't fixed in place. They can move around all the time. They localize, so they can't move from this one to that one over there to that one over there and conduct electricity. But within the molecule, they can move around in their energy levels. And so you can have at one point in time an area here that's more negative and another point in time where it's more negative on this side. So the more electrons you've got, the more you've got this mass of electrons that can change direction. So let's look then at we've got 2 types of intermolecular forces. The first one is what we call the van der Waals. So we find this both in polar and non-polar molecules. So it applies to all those atoms, molecules we had there. the size of the molecular dipole. So if it's a very polar molecule, then it's got a bigger molecular dipole. And so that will make the attraction stronger. The mass of the molecule, as we saw with carbon tetrachloride compared to methane, they were both nonpolar. And the number of electrons ties on the same way, and then the shape. The shape explains why oils, for instance, are often liquids. By oils, I mean, for instance, your sunflower oil or that sort of thing, because the shape of the molecule tends to be more crooked than the saturated fats that you find in animals and so on. They tend to be more straight, so they can pack more closely and form stronger bonds of attraction, whereas the plant ones tend to be more crooked, so they can't pack as well, and so it's got a lower melting point. So here I've tried to show not a very big dipole, and then here a much bigger dipole, so the force of attraction is stronger. And then the other one that you need to watch out for is the hydrogen bonding. Now the hydrogen bonding is important in certain types of molecules, and that's when you have, and I've stated it there, a hydrogen atom must be bonded to either N or O or F. And what is important about those three molecules? Those three elements, sorry. N, O, and F. And in a way I've actually got it there, so it's a bit of a redundant question. Those elements are very electronegative. So if they're very electronegative and they're bonded to hydrogen, where do you think the shared electrons are? Closer to the hydrogen or much closer to the N, O, or F? So one of these, it's closer to the N, O, and F. Okay, and because what is hydrogen? Hydrogen is one proton and one electron. That's all what it's made of. So if you take that electron away closer to the other atom that it's bonded to, all that's left of the hydrogen is a proton. Now, do you think a proton is, well, that's actually a poor question. I was going to ask, is it positively charged? A proton is positively charged. And if it's not shielded by any other electrons, you've got this really very positive charge that is now going to be attracted to anything that's negative around it. So that's why we have hydrogen bonds that are pretty strong. Now, the hydrogen bond is not this covalent bond. Okay? The requirement for hydrogen bonding to occur in a molecule or between molecules is that it has to have a hydrogen attached to the electronegative oxygen. But the hydrogen bond is actually this pink thing that I've tried to show here. Okay? So it's the attraction between this, what we call naked proton. Okay, remember the electrons are being pulled very strongly to this oxygen. So this is like a naked proton, and it's just looking for something that's negative around it. And oxygen, if you drew the Lewis structure of oxygen, how many lone pairs of electrons does oxygen have? Does anybody want to have a guess? If you sketch out, it's got oxygen's got 4 pairs of electrons, and it's got 4 lone electrons, but it's got 2 lone pairs of electrons, because it's got, remember, oxygen has to have an octet. It's got to have 8 electrons around it. It's got 2 in this bond and 2 in that bond, so that's 4. So the other 4 electrons are sitting as 2 lone pairs, because electrons are always paired. So there's 2 over there and sort of 2 over there, all repelling each other as far away from each other as possible. So these lone pairs sitting on the oxygen get attracted to this proton that's sitting there just ready to be attracted to something. So just be very clear when you explain what a hydrogen bond is. The condition required for hydrogen bonding to occur, you need this OH covalent bond, or NH or FH, but the actual hydrogen bond is between that hydrogen and then a nitrogen or oxygen or fluorine of another molecule. So if you don't think you can explain it in words, draw a picture like this and label this hydrogen bond. So it's very clear to the examiner or to the teacher that you know that the hydrogen bond is between the two molecules and not this covalent bond. Is that clear? Okay, so it's very important that you describe that clearly enough. Stress, it's another molecule that attraction is. And as I say, it's a pretty strong attraction because we've got more or less a full charge on this hydrogen here, proton, that's being attracted. So it's a much stronger sort of separation of charge, so it'll be a much stronger attraction than what you would have in other places. And because of that strong attraction, that hydrogen bond is quite difficult to break when you want to dissolve something. So when we discuss solubility, not every polar substance dissolves in water, but certainly every polar substance that can form hydrogen bonds with water is going to dissolve in water. So going back, and here I'm trying to show, this is formaldehyde. Can formaldehyde form hydrogen bonds between formaldehyde molecules? So in other words, if I've got pure formaldehyde, will there be hydrogen bonding between those molecules? So nobody wants to have a go? Okay, there isn't any, because these hydrogens that I've got in my formaldehyde molecule are not covalently bonded to an N, O, or F. They're bonded to a C. So they're not bonded to this oxygen. So I'm not going to have hydrogen bonding between formaldehyde molecules. So do you think formaldehyde is going to have a low boiling point or a high boiling point? Does anybody want to have a guess? Okay, it actually has a low one because it's only got the van der Waals forces of attraction between the molecules, just for pure formaldehyde. It doesn't have any hydrogen bonding. Water, in comparison, has a much higher boiling point. Talking about intermolecular solids, I'm not comparing these with metals and ionic solids and so on. Water would have a much higher boiling point because you've got to break those van der Waals forces of attraction as well as these hydrogen bonds. But formaldehyde is very soluble in water. Okay, this is the way you, it's formalin, you may notice that. It's what you use to preserve substances. Okay, because water can form a hydrogen bond with it. So if a molecule does have oxygen, nitrogen, or fluorine with it, then a substance that can form hydrogen bonds can form hydrogen bonds with that molecule. So formaldehyde can't form hydrogen bonds to another formaldehyde, but it can to a water molecule because water can form hydrogen bonds. Does that make sense? Okay, so if I went back to these again, okay, would carbon tetrachloride be soluble in water? Well, let's first ask, what sort of intermolecular forces of attraction is there in carbon tetrachloride? Is it van der Waals or van der Waals and hydrogen? So you can just say if van der Waals VDW or VDW and H. What do you think? VDW, and VDW only van der Waals. Okay, and the reason why it's similar to ethanol and boiling point is because those van der Waals forces of attraction in carbon tetrachloride is quite high because of its much bigger mass. There's a big difference in mass between these. Okay, this one is would be close to 200, whereas this is around about 50. Okay, so it's about 4 times the mass. Will carbon tetrachloride dissolve in water? Actually, it won't. The reason being to separate the water molecule so that the carbon tetrachloride can get in between and so dissolve, because what happens when something dissolves is a substance has to go and mix completely with the solute and get between the solute molecules. So the energy of attraction between the solute molecule, like carbon tetrachloride, and the solvent molecule, those attractions formed, that energy must be sufficient to break the attraction between the solvent, so between water molecule and another water molecule, and as well as between the carbon tetrachloride and carbon tetrachloride. Now, between water molecules, we've got what sort of strong intermolecular force of attraction? So remember, we've just got the van der Waals and we've got the hydrogen bonding. So water has both of those. So we've got to break those very strong hydrogen bonds between water molecules. And the attraction between a non-polar carbon tet just can't form the same strength of attractions with water. And so it can't break those hydrogen bonds, so it won't dissolve. Okay. What about, though, ethanol? Ethanol we know is polar, and it's got a similar boiling point. What sort of intermolecular forces do we find in ethanol? So VDW or VDW and H? So Nicholas is typing. Now a few of you are typing. Okay, so we've got ethanol is got oxygen, right? And we have a hydrogen bonded to that oxygen. So remember what we said, if we have a hydrogen bonded to an oxygen, nitrogen, or fluorine, we have the ability to form hydrogen bonds. So that is not a hydrogen bond in itself, but it means ethanol can form hydrogen bonds with another ethanol molecule or with water or with whatever. So that's why it's got a relatively high boiling point, because yeah, okay, Nicholas, Adobe's really starting to give problems, and I'm not quite sure why. So I have asked our IT department to look into it. So what we've got here is then a relatively high boiling point, because ethanol can form van der Waals forces of attraction and the stronger hydrogen bonding between molecules. And of course, it can dissolve in water because it can form hydrogen bonds with water, so the energy released from these new hydrogen bonds being formed is enough to break the old hydrogen bonds, because they're all similar in energy, and so it'll dissolve. What about ammonia? Okay, ammonia is a little bit lower. Okay, well, a fair amount lower actually, but it's a much smaller molecule, much lower mass. It's only about 17, and I said that's about well, it's around about 50, it's slightly under actually. So this one's quite a bit smaller. So the van der Waals forces are not as strong, okay? And however, it's still a lot higher than these over here, because this is actually a smaller molecule than that, believe it or not, because this one's run about 32, this one is only 17. So why is ammonia so much higher than oxygen? Does anybody want to have a go? Okay, ammonia's, remember we said the ability to form hydrogen bonds is when hydrogen is bonded to an electronegative oxygen, nitrogen or fluorine. So here we've got hydrogen covalently bonded to the nitrogen, and that means that the ammonia molecule can form hydrogen bonds with another ammonia molecule. And those are strong forces of attraction, so to melt something we have to separate those particles, and that is going to require more energy. Okay, and these are non-polar, and I think let's just go now quickly through it. What are the types of intermolecular forces in oxygen? Only van der Waals, because it's can't form hydrogen bonds. There's no hydrogen attached to that oxygen, so we can't do it. Okay, and it's a very small molecule, and it's only weak electrostatic forces between the oxygen. Now you do know oxygen can dissolve a little bit in water. I mean, that's how fish breathe, okay, because there is oxygen in the water. And that's, again, that little bit of solubility is, remember, the water molecules can form a bit of hydrogen bonding with the oxygen. But of course, oxygen can't form hydrogen bonds within itself. Okay, the next one is the same thing. Van der Waals, it's a small molecule. This one's 18, so it's very similar to that. It's just this one's non-polar and that one's polar and can form hydrogen bonds. So that's why there's this big jump. And so we still have very weak electrostatic attractions between the two molecules, well, between the molecules in the substance. Then we get van der Waals and hydrogen. It's still a small molecule, so there's not a big jump, but it is still a big enough jump. And I've called it weak. I mean, I'm talking about hydrogen bonds being strong, but remember they are quite weak compared to a covalent bond or an ionic bond or a metallic bond. So I've called it weak electrostatic attraction because I'm also comparing it to ionic and covalent. And those are strong electrostatic attractions. Ethanol is very similar to ammonia. It's a bigger molecule. And then we've got this very big non-polar molecule. It's only got van der Waals force of attraction, but because it's a large molecule, it's got weak electrostatic forces. In other words, it's stronger than those down here, and a relatively strength, but it still won't dissolve in water because it can't form the attractions between water and the carbon tetrachloride. Okay, so what I quickly want to do is look at last year's paper, just some questions out of there that relates to this. So there was a question like this that was up to a merit level question. If you got everything correct, you got merit for this part. So complete the table, and you have to say the type of solid. Okay, so by type I mean, is it an ionic substance, a metallic substance, a giant covalent network substance, or a molecular substance? The type of particle in that substance, so is it cations and anions? Is it metal atoms, ions, and the delocalized electrons? Is it non-metal atoms? Is it molecules? And the attractive forces between the molecules is it a metallic bond, ionic bond, covalent bond, or intermolecular forces of attraction? So that's the question, and here's an example of a person that got excellence. So do you know, by the way, you can go into the NZQA site and look at past papers and exemplars to see how students in the past have answered those questions and what mark they got? Do you know that you can use that to help you, especially when you're revising for exams? Yes, you did. Okay, it's a very good resource. So can you see here they've said that's a metallic, that's a molecular solid, 3D covalent network solid. Can you see this person who got excellence overall? Can you see how specific he is? An ionic solid. Okay, he just said ions, he didn't say cations and anions. And he said atoms there, and they accepted it, so that's fine. And as I say, there's always debate amongst the metals anyway. But you can say metallic bonding. Okay, there he said weak van der Waals, or you could have just said intermolecular forces, covalent and ionic. Okay, he did say sometimes strong and sometimes weak, but the question didn't particularly ask for that. Okay, and those two dots, if you want to know what they mean over here, that means the examiner has given them a merit level for that question. And so, some questions are only achieve level and some questions are only merit level. So don't think, oh, you got it all right and you got merit. That's because this question is a fairly recall. It's not in-depth explanation. Now here's something where it says phosphorus trichloride is a liquid at room temperature and does not conduct electricity. So explain these two observations in terms of particle structure and bonding. So remember what I said about the macro, the micro, and the model. Okay, here you don't do too much of the model, although you could have drawn a Lewis diagram, I suppose, a Lewis structure if you wanted to. But can you see he first starts off by saying what sort of substance it is? Okay, it's always a good idea to start off with that. So it's a molecular substance. Can you read this, by the way, or is the writing too small? I was a bit worried about that. You can read it. Okay, fine. Okay, so he's saying what the substance is. So even though it was, may have been in the table above, he is spelling it out. And can you see anything that's underlined is contributing towards your overall grade for this question? Okay, this one isn't underlined. PCl3 is a liquid at room temperature because he's simply repeating the question. And you could have just simply skipped that because it's in the question and just said it has a low melting point. And then do you notice he's saying the strength of the attractive forces holding the molecule together? Now that wasn't underlined, which I thought could have been, but what they really wanted here about the energy. So the stronger the attraction, the more energy is required to break those bonds. Okay, and I'll show, can you see there's 3 dots over here? So he got excellence for this question, and I'll show you another one where they just got merit. So he's talking about the energy, lots of energy needed to break those intermolecular forces of attraction, and little energy required, so it has a low melting point. Okay, and then he's got to explain, don't just talk about the liquid, talk about the other macro property, which it doesn't conduct electricity. So you've got to basically say it doesn't have any charged particles that are able to move through the substance to conduct electricity. So something along those lines. So he's spelt it out. It's, the electrons are localized in the PCl bonds and so on and so forth. Okay. So there's no free moving charge. Compare this to a merit level question. Okay. He also started off with it's a molecular solid, and he's also said it's weak intermolecular forces. So notice he used weak intermolecular, not van der Waals, but both are acceptable. Okay. In fact, intermolecular are broad because it also includes hydrogen bonding, whereas you could argue that van der Waals doesn't. Okay, he's identified the molecules as the same as that. But do you notice he doesn't actually spell out the energy? He just simply says that even at room temperature they can be broken. But he doesn't talk about that it's the ambient energy at room temperature that breaks those intermolecular forces. So he hasn't referred it to energy. Okay, now he's repeating this in the question. It doesn't conduct electricity, and he does explain it doesn't have any free particles, like electrons. Ideally, should have said like delocalized electrons, or at least he spells out ions. And he just got a merit. So do you see the difference about the level of detail you need to have in your answers? So you need to talk about what bonding can form and energy for breaking and making bonds and so on. Okay, so what I'm going to do, because I wanted to get this onto bonds having energy, there are basically, as far as chemistry is concerned, 3 types of energy. Kinetic, that's the particles moving around. The faster they move around, the bigger the kinetic energy. And normally the faster they move is because of the higher temperature. So temperature is directly related to kinetic energy. The potential energy. Now I've said the chemical energy, potential energy stored in bonds. That, strictly speaking, is not true, because you give off energy when you make a bond, and you require energy to break that bond. So it's, strictly speaking, not stored in the bond. It's sort of stored in that whole stability molecule. But it is one way of visualizing it. And then we've got heat energy. And heat gets related also to kinetic energy, because if you give off heat energy, it makes things move, it raises the temperature, it makes things move faster, and so on. So we've got 2 situations where we have a substance that is giving out heat, thinking of heat energy. Enthalpy is a word you have to learn for this year. It's just a fancy word for heat, enthalpy. So if my substance is giving out heat, we say it's exothermic. So if something is giving out heat, it's losing heat because it's radiating it out, it's exothermic. If something is getting cold, it's actually dragging in heat, and so it's what we call endothermic. So we don't say, oh, don't open that window, you'll let the cold in. It doesn't work like that. It's either the heat going out or the heat coming in. You don't have cold moving anyway. So this change, remember that we're either radiating heat or we're bringing it in. So it means the energy, the heat is changing. And the way we work it out is we say for a reaction, so if I mix 2 things together and suddenly heat is given out or suddenly heat has been sucked in, for that reaction, we look at the energy of the products and the energy of the reactants. And then we say, okay, we had this much energy involved in the reactants, this much in the products. The difference is the energy that's going to be given off or taken up. Does that make sense? In fact, if I do those diagrams, here is a reaction proceeds or a reaction coordinate. It's not necessarily time, because it's not related to seconds at all. We're just saying it's going from one point of the reaction to another. So when you label these diagrams, make sure you have a label for the x-axis. And then energy is always on the y-axis. So if I've got a high level of energy in the reactants, so they've got lots of energy, and my reaction occurs and my products have low energy, that difference in energy, has it been given off or taken up? Anybody want to have a guess? Given off. Correct. Because I had lots of energy, now I don't. It's got to have gone somewhere, so it's been given off. So is this an exothermic or an endothermic? You can just type EX or EN. Exothermic, great. And this is where my reactants didn't particularly have much energy to start off with, but then I made them do a reaction, and now the products have got lots of energy. where I must have got that energy from somewhere, because we can't create or destroy energy. It must have come from somewhere. And that means it must have come from the surroundings. So I'm dragging energy into my reaction system. So can you see this will be an endothermic reaction? So exothermic is when energy of the products is less than the reactants. Endothermic is when energy of the products is more than the reactants. Does that make sense? Is that clear? Okay, right. So basically I just want to finish off with this as an example. You know, I was talking about the sort of, there is energy, if you like, stored in the bonds, but you've got to be clear that breaking bonds requires energy. Okay, so that's, remember when I said when something dissolves in water, if I've got to separate two water molecules to let a solute in so it can dissolve, I've got to break that hydrogen bond between those water molecules. And that needs energy. It's like if I've got two magnets attracted to each other, I've got to pull on those two magnets to separate them. So if I'm breaking an attraction, I have to add an energy. Whereas making bonds releases energy. So you know, if you've got two strong magnets, north and south pole, you'll feel that pull and then it'll snap together. So it's, you know, energy will be released when you make bonds. So we can work out the energy of the products and the energy of the reactants on an average scale, okay, by using average bond energies. So chemists over the years have tried to measure the average energy of a BR-BR bond, or a C-C bond, or a CO bond. So there's all these tables that you can look up for the average energy of a particular bond. And then you can work out whether it's exothermic or whether it's endothermic. So here's an example of ethene reacting with bromine gas, and I'm forming the bromoethane. Okay. Now there's two ways to approach this, and when I looked at the exam papers that were given, because this is from last year's exam as well, they broke all the bonds and made all the bonds. So that is one way of doing it. So can you see, you can either say, right, what's different between this side and that side? I've had to break this double bond and make that single bond. So I've broken one double bond and I've made a single bond. I've also had to break this bond, okay, and I've had to make a CBr bond and a CBr bond. So I've had to make two CBr bonds. So we could just look at the bonds broken and the bonds made and we'll come up with the same answer. Or we could break that CH, that CH, that C double bond, C, that CH, that CH, that BR. So break every single bond amongst the products and then make every single bond here. So you could make one CC bond, 4 CH bonds, and 2 CBr bonds. Now when you do this, I strongly recommend you just circle the bonds, because it's so easy to miss a bond when you go trying to count which bonds are being broken or made. So here's an example of the question. Okay, I've just spelt it out here. Calculate the enthalpy change. So what is it exactly, well, in terms of average, and you could also see if it's exothermic or endothermic. So here's an example of the student that got excellence for this. So all of them actually did this. He listed all the bonds that occurred in the reactants. So can you see here, there's all the bonds being broken. So that's his big total of all the bonds being broken. Now these are all the bonds being made. Now can you see he has worked it as bonds being made on negative because they're releasing energy. Okay, and so he's listed that bond, 4 CH bonds and 2 CBr bonds. And then he's just added them together. So he gets minus 109 kilojoules per mole. So you can see he's got his unit and he's got his final answer. Okay, the others did things slightly differently, but was also accepted. Okay, you can see there's 3 dots there. So what they did, they introduced a formula of, remember this just simply means heat of reaction. H is enthalpy, R is for reaction, bonds broken subtract bonds made. So here are all the bonds being broken, and you can see they've worked out all of them, and all the bonds being made, and they get to the same answer. And the third person they had up there as well said bonds broken subtract bonds formed. So I like the first method the most. So if I go this one, because I like showing all that and all that on, everything on the right hand side and everything on the left hand side, and then just adding them together. But I think I've given different methods in the booklet, and you can decide which method you would like. Do you all have this new chapter in the CH2044 booklet? Because the old version doesn't have it. So if you don't have bond energy in the booklet, then please contact your teacher and ask them for that lesson on bond energy. Okay, so basically I want to stop there because we are already 12 o'clock anyway. You should now know nearly everything to do with the 2.4 standard. We'll just do one last lesson next week, and then we can move on to, say, the organic standard. But are you all clear on now the 4 different types of solids, their properties and how to explain them? Okay. Right. Okay, so it'll be just calculations next week. And